So this is the first lecture on probability theory. So we basically follow the book by V.K. Rohatgi, Introduction of Probability Theory, Mathematical Statistics. So the probability is on the first 5 or 6 chapters. First 6 chapter we complete in this course. So what is probability? Before going to probability, we have to know what is random experiment. So everything starts with random experiment. So what is random experiment? Random experiment is sometimes it's called statistical experiment or random experiment. So the name is random. This term is actually some undefined concept, random. You can't basically define what is random, or sometimes called statistical. Statistical experiment. So then it is experiment and it is random. In what sense it is random? So number one, all the outcomes of this experiment are known in advance. Something like, say, tossing a coin. If I start to toss a coin, then what are the all possible outcome is either head or tail. So there are 2 possible outcomes. If I toss a coin twice, then there are 4 possibilities: head, then head, head, tail, tail, head, and tail, tail. Similarly, if I throw a die, then the 6 possibility 1 to 6. But all the outcome is known. But the particular outcome, for any experiment, the particular outcome, what outcome will be happen in the this experiment, that is unknown. If it's known, then it is nothing about the random. That's why it's called random. So there are several possibilities. It may be head, it may be tail, but we don't know which will come. One of them will come. So, so particular outcome is not known. In advance. And the next one is very important. The experiment can be repeated under identical condition. So the experiment, this is very important. This is important. The experiment can be performed, can be repeated under identical condition. What is the meaning? That means meaning is that if we toss a coin, we can repeat that experiment several times. It is not that just you have a coin with mud, say glass, and you toss the coin and it is broken down. That is not a random experiment. Once it's broken down, you can't broken, then you can't repeat the experiment next time. So that's why this experiment is not random. So you have to repeat. We have to repeat in identical condition. Otherwise, we can't talk about the probability. It's just a once, then we can't talk about the probability. So you should repeat under the identical condition. But some relaxation is there. We are not going into that. So if assume that experiment can be repeated under identical condition, we have to assume that. So this 3 assumption on the random experiment, like tossing a coin. So example like tossing a coin, or throwing a die, or or tossing a coin twice. Like that. Now, set of all such outcome, set of all outcome is known as sample space. Set of all outcome comes like is called omega, capital omega. This is sample space. Now we need some collection of some subset, which is called event space, and we know this is a sigma field. We have to take this as a sigma field. In measure theory, we know there is a sigma field. So take a sigma field. Script F S is a sigma field. Sigma field of subsets of that script omega. So is a collection of subsets. So that means it's a set of subsets. So that means the set of event that the subset of this omega is called event. Not the any subset, the subset which collect in the sigma field. So any element of this is called event. So any element A is known as event. Sometimes this is known as this sigma field is known as event space. Events known as event space. So this is known as event space, or sometimes event is called event point, either event or event point. Similarly, omega is sample space, and any element of omega, that omega belongs to omega. So omega is an outcome. Or sometimes called sample point. Sample space, sample point. So elements are point and that set are space. So sample point, collection of all sample points is sample space, and collection of all event or event point is event space. And that any subset of omega may not be event, is a some suitable collection of omega, subset of omega. So that is called event space, and that should be a sigma field over or sigma algebra over capital omega. Now we know what is sigma field. So what is sigma field? We know this. If A is in the sigma field, then A complement is also in the script S. And this must be non-empty. That script F is non-empty. At least one element will be there. So omega and the phi set will be there. And the other conditions is if A1, A2 dot is a sequence of set in this script S, then that union must be in this collection. And we know the from these two we can easily there is a result that the intersection is also there. So result is if A1, A2 by De Morgan's law, this intersection is also in this set, in this collection. Now this is the setup. Now we are going to the probability concept. So before going that, we have to know what is called the intersection of the sequence of set and intersection of the union of sequence of set or lim sup or lim in. That we discuss in the measure theory series of lecture. In that measure theory video, we can find that what are the sequence of set and what is that limit and what is the lim sup limit and what are the intersection of countable intersection, countable union that we discuss in the measure theory class. So we will not discuss here. We now going to the probability. So what is probability? Now this is something like measure. Probability also a measure. So now the definition of probability is this. The formal definition is this. So let omega and script S, that is a sigma field, be a sample space. So be a sample space. Sometimes sample space is written not only this omega with that script S also. So we have to describe all the set which are the event of this sample space. So sample space means it is just sample space omega as well as that sigma field, the event space. So it is a sample space and event space. So sample space sometimes is called sample space. This is this collection is the pair is called sample space. Is now a set of function. Now a set of function we define this probability is not a single function, it is a set of function. Any function which satisfy the following condition is a probability. Set of function P is a function, so probability is a function defined on that script A. Remember, this defines on script S. It's called probability or probability measure. It's called probability or probability measure. Probability measure, or simply you can call it just probability. Since it is a measure, so it is probability measure. You can just call it probability. Satisfy if it satisfy the following condition. What are the conditions? This condition number 1, the probability of A must be greater than or equal to 0 for all A. So probability is like a function. It's a function from that is actually it is a function from sample space to 0, 1. The condition 2 is the set of this whole thing is 1. That is important. Otherwise, it can be any measure. For any measure, the second condition is not true. And the third one is always true for any, also true for the general measure. If A1, A2, dot, AN, that sequence is in script S, we know that union is also in script S, but take that as a disjoint collection. So this is phi for all I not equal to j. For I equal to j, it can't be phi. So this is phi for all j. For I equal to j, it can't be phi unless the both this aj are phi. Then what happened? Then the probability of that union of I equal to 1 to infinity ai, that is equal to sum over I equal to 1 to n probability of ai. So just the sum. So if disjoint is like a measure. And that 3 is called countably additive property. This is called countable additivity. This property is called countable additivity. Sometimes finite additivity is there for some of union of finite set. That will be the sum disjoint finite set. That is called finite additivity. Is countable additivity. Sometimes we referred for measure theory is countable subadditivity. Some countable subadditivity is that union is that measure of the union is less than or equal to sum of the measure. That is countable subadditivity. But in probability, we assume that countable additivity property. So these three conditions satisfied, then it is called probability. That PA is called probability of that event A. That PA is called probability of event A. And now this triplet, we have this all three things. So one is sample space, and there's event space. The script is the event space, and that P. That triplet is called probability space. That P is probability, and that is called probability space. If I say something is probability space, that means there are three things is there. So sample space, then event space, and a probability measure. So that is in triplet we have set up this called probability space. So there are several examples of probability space. We like tossing a coin and then take this set of all subset is your event space. For finite, if omega is finite, we usually take the set of all subset as a event. The problem is if omega is uncountable, then we can't take as that all set as all subset as a event. That is a problem. We discuss in major theory class that there are several other probability thing other than that So we have some non-trivial example like that. So one thing is example like a tossing coin, and then we take another example. Say omega is say 1 to 3 set all positive integers, and script is a power set of s omega, that is a collection of all subset. Then we define p on the 0 1 like that. So probability of say I, the set containing only I, is 1 by 2 to the power I. What is that? That means the probability of set containing 1. Remember that not probability of 1, it is probability of set containing 1. Not probability of head, is probability of set containing head. We talk about the probability of head, but it's actually student speaking, it is wrong. We have to say probability of set containing head, because probability not defined for an outcome, probability defined for an event. So head is the outcome, but set containing head is the event. So you should say probability of set containing head, but we usually we abbreviate the abuse of notation, and we call probability of head. The meaning of probability of head, meaning it is just probability of set containing head. So probability of set containing I is 2 dy, that means probability of set containing 1 is half, probability of set containing 2 is 1 by 4, probability of set containing 3 is 1 by 8, and you can talking about all these things. The same probability of set containing say 2, 4, and 7. You just add all these things, 1 by 2 to the power 2 plus 1 by 2 to the power 4 plus 1 by 2 to the power 7. Just the countable additivity, or here it is just finite additivity. So this defines the probability on this sample space. Now another example is like that. So take this as a all positive real number, set of all positive real number, and this script is a Borel sigma algebra over that. On this, all this positive Borel sigma algebra over the positive set, on define on that. Now we define P in this Borel sigma algebra over omega to 0 1 like that. For each interval, say take each interval, I is an interval, interval and I is subset of this. So it is a interval, open or close, whatever. We take that probability of that interval, and this is a Borel set. This I belongs to this script B. So this is actually from 0 to so positive real number. It can be open, it can be closed, half open, half closed. We define the probability of that interval. Any interval is like that. This is the integration over that interval, e to the power minus x dx. Now, what is the probability of the whole this? This is just probability of 0 to infinity. Remember that integration from a to b is need not be closed or open, whatever. If it is a closed, it's open, is the same. We prove it in major theory that that integration, that Riemann integration, whatever the is closed interval AB or is a open interval AB or semi-open interval AB, semi-closed, that integration is same, because the integration from A to A is in a single point, it is 0. So this is minus e to the power x dx, so that is 1. So this follows satisfy the first condition. It is a positive, and is a for countable disjoint union of interval, that will be this. There's a sum. So this defines a probability. This defines a probability. Now remember that we define that probability in only for interval, but we know the Borel sigma algebra over that positive real number can be constructed using that intervals we discuss in major theory, using that intervals and that complement and intersection and union. So ultimately we can find the probability of any Borel set using the probability of only that probability of these intervals only. If I know that what are the probability of the intervals, then we can find what is the probability of any set, any Borel set. Now there is a theorem. This theorem or result is very trivial. It's a school level theorem. If A is a subset of B and AB both are in this S, that means it is even, then probability of A is less than or equal to probability of B. That is trivial. It's just you consider A B like just A union B minus A, and then probability of this is just probability of A plus this, and probability of B is, sorry, this is probability of A plus probability of this part, and this is positive, so this is probably greater than equal to A. So this and then we have this result also. This is theorem is very easy. If you take any two set, may not be the subset or may not be disjoint, then probability of A union B, we know this. This is probability of A plus probability of B minus probability of A intersection B. That is trivial. And then we have this theorem: if A1, A2, A3 dot 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 AN are finite Lie set and may not be disjoint or may not be subset of any other one, then probability of the union is just less than or equal to sum over I equal to 1 to n probability of AI. Then this is easy to check, and probability of A complement is 1 minus probability of A. That is also easy using that summation part. Now this theorem is important. This is called principle of inclusion exclusion. The principle of inclusion and exclusion. So if A1, A2, AN dot 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 finite color finite when you say event is element of that script S, that is sigma algebra event space, that A1, A2 are event, then what is the probability of their union? So probability of their union is, this is sum over this sum over I equal to 1 to n probability of AI, and then minus sum over I equal to I less than j, I less than j probability of AI intersection AJ. So intersection of two at a time. Then sum plus sum over I less than j less than k, then probability of AI intersection AJ intersection AK, then you take 4 at a time and then plus 5 at a time, and so on and so forth. And the last thing is that that should be minus 1 to the power n plus 1. If n is odd, then it is plus, and if it is even, then it is minus. So probability of that intersection of all this set I equals or k or maybe t equal to 1 to 80. Don't confuse with that I. You can write I also here. So whatever. You can write probability of I. Okay, write probability of I. That intersection of I equal to 1 to n. Remember this I and that I in this previous, that AI, these are different. Don't make confusion. It's a different term, so you can use I, J, whatever. That I and the other term is summation I, that is not same. So like summation over I equal to 1 to n AI plus summation over I equal to 1 to n, 1 to say M, BI, that is that two I are not same. So like that. So this is the principle of inclusion exclusion. What is the proof? Proof is by induction. You can use induction in any book. You find this induction proof, but here is another proof like that. So it is like a Venn diagram thing. So we have this thing, that, then one more set is this, something like that. There are so many sets. Now consider a term, an element of this omega which belongs to exactly one of them. Whatever, if it is exactly one of them, just exactly one of them, some omega which is belongs to exactly one AI. So set of all omega which is exactly in one AI. So omega belongs to is for exactly one I, for exactly one I. Then what happened? Then we count that element in the left side, that union, once, because it is in exactly one I, one AI. So say it is in A1. So we count in union is once, we count is one, and in the right hand side we also count in the one. Just equality of A1, we count in that case. Now take an element which is in exactly in 2, some AI intersection A1 intersection A2, and that element we count left side as exactly 1. Remember, is union, it is we count exactly 1 time. Now what happened in the right side? Right side we count in the summation of PI we count it twice. Probability of A1 we count there, probability of A2 we count there. So we have to take the difference. We have to take the intersection, and that intersection we have this element omega in intersection exactly 1. So we count here twice and we take this. So for 1 it is just 1 equal to 1. For if it is in the omega is in the 2 set, exactly 2 set, then it is a 1 equal to 2 minus 1, like this. So in the left side is 1, right side it is count twice and minus 1 time. Now if it is exactly 3 in the 3 element 3 set, then left hand side is always exactly 1. So in right hand side, once we take the summation probability of AI, we count twice. Now we take that intersection A1 intersection A2, A1 intersection A3, A3 intersection A2. So we take two at a time intersection, we count 3. So minus 3. Now 3 at a time, A1 intersection A2 intersection A3, we count there exactly 1 time. So it's like that. So and for 4, if it is exactly 4 many set, what happens? Then it's a left hand side is always 1, the right hand side is 4, then 2 at a time. So A1 intersection A2, that's 6 many such a set. So that's minus 6, then plus 4, because 3 at a time, if any element in the 4th set, A1, A2, A3, A4, then if you take 3 at a time, A1 intersection A2 intersection A3, you count there. A1 intersection A2 intersection A4, you count there. A1 intersection A3 intersection A4, you count there. A2 intersection A3 intersection A4, you count there. So 4 when you count, and then you just take 4 at a time, that is minus. So again, the same number of element counting in left side as well as in the right hand side. So for in general, if some element in R many set, what happen? If some element in R many set, then in left side is just exactly 1. In right side, one at a time summation, that is in R many set, it is RC1. If 2 at a time, then it is RC2. In 3 at a time, it is plus RC3. And we know this summation is exactly 1. Actually, it is exactly 1. This last word, what RCR is odd, then it is minus 1, so it is R plus 1. So it is RC1. Sorry, R many set. Yes, it is R many set. Right. It is if it is collection in the R many set, A1 A2 AR, then we have this set in right. And we know this is true because RC0 plus or minus, take that side, RC0 minus RC1 plus RC2, we know this is actually 0. We know this in binomial theorem, this addition is 0. RCR, this is 0. So from that, so this is one proof without any induction thing. So this inclusion exclusion thing. Now there is one inequality called Bonferroni inequality. Bonferroni inequality. So take any events A1, A2, AN. These are events. that means is a subset of is the element of that event space, that sigma algebra script test. Then bound-frame inequality says that their union is, that side is you can use it by induction, prove it by induction, that sum over probability of AI, that we can use by induction, and this is greater than or equal to sum over I equal to 1 to n probability of AI minus, if you are 2 at a time, then it will be lesser. Sorry, this is probability of AI, then minus probability of I less than j, summation I less than j probability of AI intersection is. So what is the idea? The idea is the same here. If you take this term only, if you take this term, then the right hand side is bigger. If you take one more time, then it is minus, so it is left hand side is again less than the right hand side is less than left hand side. If you take one more term, then right hand side is bigger than the left hand side. If you take one more minus sign, then the right hand side is lesser than that left hand side. That means it includes something big, then we exclude, once I exclude, we exclude extra, then it is less, then we again include 3 at a time, then we have extra thing, then we have to exclude some other thing 4 at a time, then we have to include 5 at a time, then we have to exclude 5, 6 at a time. That's why it's called inclusion exclusion principle, and ultimately at the last stage it will be equal. So, and you can prove this is by this, not only by induction it will be slightly complicated, and if we use this combinatorial argument like NCR, that part, that for how many each element in how many set, that will be easier to prove or things, rather than that complicated induction thing written in the book. Now, one thing is one more way called Boole's inequality. This is also very important. This Boole's inequality. Boole's inequality. This is probability of for any two event A and B. So you just A and B. If you forget to write that A and B in belongs to script test, you assume that this AB are event by default, which is bigger than or greater than or equal to 1 minus probability of A complement or probability of B complement. So this is sometimes called Boole's inequality. And this there is a corollary of this. Corollary is this, that probability of intersection of all AI are in a script test is greater than or equal to that 1 minus probability of summation probability of AI complement, which is actually, if we write in this sense also, that sum over probability of AI minus n minus 1. You can write this as probability of A plus probability of B minus 1. You can prove it by induction. So this remember that there are two inequalities. So one is for union, the upper bound for the union is a lower bound for the intersection. So when these two are useful, basically, if all the probabilities of AIs are very low, then this upper bound of this union is important, because if the probability of AIs are high and this summation over this PIs is greater than 1, there is no, it's just a trivial thing. Some probability is less than or equal to 5, that is trivial. That should be true. Some probability of, if this sum, say sum over I equal to 1 to n, probability of AI is say 5, that sum is 5. Then what is this inequality? When one friend inequality says the probability of union is less than or equal to 5, that is trivial. We know the probability should be less than or equal to 5 because it is less than or equal to 1. So for big, if the probability of AIs are large, then it is not important. In that case, the Boole's inequality is important. in that case the probability of A complement is small, then we can use this thing. On the other way, if the probability of A complement is high, is very close to 1, that is the Bose inequality is not important, is not useful basically, is trivial. And if in that case bond friend is important, since the probability of AI is small, so there is a upper bound for that. So we just write this in for the two thing, we can set only for two set. So probability of A union B, that is less than or equal to probability of A plus probability of B. Right, and this is less than greater than or equal to, just write is, so probability of A union B, this is actually less than or equal to probability of A plus probability of B. Now this is bigger than probability of A. We know the probability of A union B is bigger than probability of A, as well as probability of B. So this is maximum, this is greater than the maximum over this either probability of A and probability of B. Then this maximum is the, if say probability of A is the maximum, then which is the bigger than minimum of that, probability of A and probability of B. Now their intersection must be less than that. So because the probability of A intersection B, so A intersection B is a subset of A as well as subset of B. So that's why the intersection is probability of this intersection is less than that. Now again, what is that? For by Bonferroni inequality, this is greater than or equal to probability of A plus probability of B minus 1. So this is very interesting result. And if probability of A plus probability of B is less than 1, then there is no need. Basically, nothing is trivial, because the left hand side, that probability of A plus probability of B minus 1 is negative. So we should take the maximum over this and 0. And similarly, if this probability of A plus probability of B is bigger than 1, this is not useful. So we should take the minimum of that. Minimum of either probability of A plus probability of B and 1. And 1. So this is interesting inequality. Now consider a probability of A is say half and probability of B is say 1/3, and if they are independent, probability of A intersection B is 1/6, and probability of A union B is what? Then it is 1/2 plus 1/3, which is 5/6, minus 1/6, which is 4/6. So if you just write this, all this probability, exactly what you get. This is 1/6, which is less than or equal to 2/6. 2/6 is the actually the 1/3, which is the minimum, and the maximum is half, that is 3/6, which is again less than the union, which is 4/6, which is less than actually sum of this minimum of these two, so it is 5/6, and this is actually it is 0/6. And you can write also 0 here, 0 greater than equal to, and you can write 1 here. It is 6/6. It's a very interesting thing. Just verify with this example. And not only for this two, this is true for n number of set. Now there is an important result, limit of the set. We know what is limit, what do we mean limit in sequence of set. So this theorem is, let An is a sequence of set, is a, let this be a non-decreasing sequence, sometimes called increasing, sequence of events in that script S. So what is the meaning of that? That is each an is in script S for n equal to 1 up to dot 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 dot, and that an is non-decreasing, that means is subset of an plus 1. Sorry, it is non-decreasing, right? It is, sorry, it will be n minus 1. Sorry, so an must be superset of an minus 1 for n equal to 1, 2, 2, 3 dot dot dot. So a1 is a subset of a2, a2 is a subset of a3 dot dot dot. So you just write a1 is a subset of a2, a2 is a subset of a3, non-decreasing. So it is like increasing. In that case, the limit n tends to infinity, probability of an is equal to probability of their union. So proof is the outline of the proof is this. We just take A as their union n equal to 1 to infinity an, and that A equal to then what? It is an plus union over all b j equal to 1 to 1 to what? Sorry, n j equal to n to infinity. So what is the idea? Idea is this. This is a1. This is my a1. This is my a2. And this portion is actually a2 minus a1. And next is a3 is slightly bigger, maybe equal a3 minus a2, like that. So that means if it is somewhere it is an, the next part is actually an plus 1 minus an. Then the next part is that an plus 2 minus an plus 1. So that we call bj. We write b, say b1 equal to a1, b2 equal to a2 minus a1, or that bj is actually equal to bj minus bj minus 1. Oh, not that, it should be b a2 b, then we say for n plus 1, start from n plus 1. Right, in that case we should write it as n plus 1, because b n plus 1 is bn plus 1 minus bn. And the idea is easy, it's b2 is then just a1 union a2. Oh, sorry, a2 is then b1 union b2. A2 is then b1 union b2. A3 is just b1 union b2 union b3. Now they are disjoint. Interestingly, bj's are disjoint. Aj is not disjoint, so bj's are disjoint. So we can use that probability result for disjoint case. So since bj's are disjoint, now the probability of A, that the limiting sense, this is probability of an, these are disjoint, plus sum over all this j equal to n plus 1 to infinity probability of that bj, that probability of bj. Now what happened? What is this? So this is probability of an plus sum over j equal to n to infinity probability of aj plus 1 minus aj, and take the limit. So this is limit n tends to infinity probability of an plus limit n tends to infinity probability of the sum over j equal to n to probability of aj plus 1 minus aj. But what's the second term? Second term goes to tends to 0. The second term goes to 0. Remember this limit n tends to infinity, this goes to 0. This goes to 0. This limit is 0. This is sum is 0. Why it is so? Because your series that from j equal to 1 to infinity, that probability of aj plus 1 minus aj, this is actually less than equal to 1, because this is just what this probability is. This is b1 complement basically. This is a1 probability of a1 complement. So this is less than equal to 1, and the series is less than equal to 1. We know what is the result. Result is if sum over ai I equal to 1 to infinity, this is a finite sequence. Its ai's are positive or non-negative terms, and there's the series is converge. If this is so, then what happens? Then this I equal to n to infinity ai, limit that n tends to infinity, this must be equals to 0. The tail must be equals to 0. For a finite sequence, the tail must be equals to 0. So that's why this goes to 0. So that means, therefore, probability of A is the union of all these things. Remember that A is the union of all this, so is the limit of that. So you got this result. Limit of probability of an, probability of an, because the second part term is 0. And this completes the proof. Now there is some two corollaries. Let an be a non-decreasing sequence, non-increasing sequence. Then this probability of this limit is limit n tends to infinity. Sorry, that probability of an, which is not, since it is non-increasing, this that in limit is the intersection now. 1 to infinity an. So this limit is now if they're non-decreasing, sometimes we write an is non-increasing, so it's a drop to a. Sometimes it's called that non-decreasing part. We write that as an up to a. So is increased to a. A is the union of n equal to 1 to infinity a. And here it is intersection, it is decreased. Non-increasing or decreasing set, that here it is a is intersection of n equal to 1 to infinity, 1 to infinity a. Now, how do you prove this? Proof is just use of that previous theorem. We consider the an complement part, and an complement part is now non-decreasing. Now we use the previous theorem. In previous theorem, limit n tends to infinity, that an complement is that union over all n equal to 1 to infinity an complement, and thanks to the De Morgan's law, this is actually intersection over all an n equal to 1 to infinity whole complement, and this is a complement. Now from the previous theorem, it is just probability of A complement is probability of limit of n tends to infinity A n complement, which is limit n tends to, which is actually what? Which is actually probability of the union over n equal to 1 to infinity A n complement, and this is actually probability of limit of n tends to infinity A n complement. Oh, right, is the previous thing, which is same as limit n tends to infinity probability of, by the previous theorem it is just A n complement. Now what is this? This is 1 minus probability of A, then this is limit of n tends to infinity 1 minus probability of A n complement A n. So just take one cancel out, and then it is implies that probability of A equal to limit of n tends to infinity probability of A. So we stop this video here. Next we in the next video we consider some we discuss on some combinatorial problem or some major theoretic problem in probability, some Bonfermi some patterned paradox and buffer needle problems, and then we go into the random variables. So up to this in this video.